Tonight, welcome to a slower universe. We are going to drift through light years, ghost stars, and the quiet architecture of the cosmos, all in a calm, sleep-friendly way. Let the weight of the day fall away. Let your breathing soften and allow these stories of space to quietly fill the background as you rest. If these gentle journeys through the cosmos help you relax or fall asleep, you can support this channel with a like and a subscribe so more nightly explorations can be made. Now settle in and let us begin. At the very edge of what can ever be seen, the universe draws a faint, silent circle around itself. Beyond that circle, nothing has had enough time to speak in light, and so the cosmos, as far as any instrument can tell, simply ends in darkness. Astronomers call this boundary the observable horizon, not because it marks the true edge of everything that exists, but because it traces the farthest distance from which light has had time to arrive since the birth of space and time. From that first burst of expansion until this quiet night light has been traveling without pause, step after step, across an ocean of emptiness, carrying with it a record of ancient events. Every ray that reaches a mirror or a sensor on a tiny world around an ordinary star has survived a journey that lasts for billions of years. The picture formed from all these arrivals is not a flat shell like a painted dome, but a three-dimensional sphere of possibility with one small planet at its center and a horizon at a distance of about 46 billion light years in every direction. A single light year already represents the distance that light crosses in 1 year, moving at roughly 300,000 kilometers per second. In that single second, it could circle a planet like Earth many times, yet it must repeat that effort, second after second, year after year, to form even 1 light year of distance. To reach the observable horizon, light must stack that span on top of itself billions of times. The mind that tries to imagine this meets only a kind of abstract haze, a sense of immensity without clear edges, and that failure of intuition becomes the first sign that ordinary human measures do not belong here. At these scales, the universe resembles a quiet geometry more than a place one could cross. The space enclosed within that horizon is filled with matter and radiation, but the distribution is anything but crowded. Galaxies appear as small knots in a vast cosmic web, each knot made of hundreds of billions of stars, and yet the average distance between these knots stretches for tens of millions of light years. Between them lie enormous voids regions where there may be only a few lonely galaxies scattered across volumes that would dwarf entire clusters elsewhere. Even the luminous regions, the massive clusters where thousands of galaxies gather under mutual gravity, seem fragile against the background of the overall structure. Threads of galaxies, walls of galaxy clusters, and hollows of nearly bare space weave together into something that looks less like a simple distribution of objects and more like a frozen pattern in an invisible fluid. Every meter inside this structure has existed for almost the entire age of the universe, about 13 and a bit billion years, and in that time, light from the most distant regions has only just arrived. Beyond the horizon, more space almost certainly continues, perhaps infinitely, perhaps in ways that current physics cannot yet anticipate. Yet no signal from there can ever reach this small region because the expansion of space itself pushes those further domains away faster than light can close the gap. It is not a wall that something might one day break through, but a moving limit written into the behavior of space-time. Over unimaginable spans of time, the observable universe for any single observer becomes a personal bubble, different for every world, defined by where and when that world awakens to look outward. The seeming center of this bubble is never special in a physical sense. Any galaxy could place itself in the middle and draw the same kind of horizon. What matters is not the location, but the fact that light connects events in a strict order, carving out a domain of what can even in principle be known. Within that domain, each ray of light carries a message from some distant surface, such as a star, a galaxy, a cloud of gas, or the afterglow of the early universe. Those messages arrive already aged and stretched in wavelength by the expansion of space. They whisper of past states of matter, of younger galaxies, of a universe denser and hotter than the present one. Taken together, they sketch a story in which gravity slowly sculpts structure from a nearly uniform fog. Tiny differences in density grow into the first clusters, then into a filamentary network, until the cosmos resembles a vast foam of light and shadow. The observable horizon, then, is not just a simple edge of visibility. It is a layered shell of time, with the most recent events nearest and the earliest events pressed against the outer surface. To look farther in distance is to look deeper into the past. There is no way to see the universe as it is everywhere, at a single moment. Every line of sight leads through a tunnel of history. That strange coupling of distance and age is the first hint of the rule that will govern every scale, to come from giant clusters to local stars and finally down to the quiet orbit of a single planet. The speed of light does more than define a unit of distance called the light year. It structures what reality can be observed at all. At the horizon, this structure becomes so extreme that imagination falters, and yet the same principle will remain in place, even in much smaller, more familiar spaces. From this silent boundary, the story begins to fall inward, moving step by step toward home. Between the distant horizon and the familiar cluster that holds the Milky Way space, arranges itself into a pattern that at first looks almost like a trick of vision. When maps from deep surveys are plotted in 3 dimensions, the galaxies do not scatter like dust in an even fa. Instead, they gather into filaments and sheets that stretch for tens and hundreds of millions of light years, creating a fragile skeleton of light. At the junctions of these filaments lie the great cluster cities of galaxies, held together by their combined gravity, while between the threads and walls open enormous voids that contain almost nothing at all. The result resembles a frozen foam or a lacework of brightness laid across a background of darkness. Every bright point in this pattern marks a galaxy, each with its own hundreds of billions of stars, planets, and clouds. Yet in the diagrams that condense them into dots, they seem almost delicate, as if a careless gesture could erase entire superclusters with a single sweep. The surprising part of this picture is not the presence of galaxies, but the overwhelming quantity of emptiness between them. On average, Even the crowded filaments contain so few atoms per cubic meter that a laboratory vacuum on Earth would feel dense by comparison. In the voids, the matter density falls even lower, approaching the point where the concept of space containing anything at all begins to lose meaning. Light still crosses these hollows, but it carries almost no message, only the stretched and cooled echo of the primordial radiation that fills all of space. When astronomers first traced this web through redshift surveys measuring how much the wavelength of galactic light was stretched by cosmic expansion, they expected structure, but many did not expect such dramatic contrasts. Great walls of galaxies appear next to seemingly bare regions, spanning hundreds of millions of light years. In those silent gaps, a single lonely galaxy may drift far from any neighbors, its light taking tens of millions of years to reach the nearest other island of stars. The visible web already reveals a universe where darkness dominates visually, but it hides a deeper puzzle. When the motions of galaxies and clusters are measured, and when the rotation of their disks is tracked, the luminous matter alone cannot account for the forces at play. Stars at the outer edges of galaxies move too fast to be held by the gravity of the visible mass. Clusters hold together despite the apparently insufficient pull of the galaxies that can be seen. To reconcile these motions with the laws of gravity, astronomers infer the presence of unseen matter, something that does not shine, absorb, or scatter light. This invisible component, called dark matter in everyday language, outweighs ordinary matter by a wide margin. Roughly speaking, for every unit of familiar atoms, there appear to be several units of this dark substance. In the context of the cosmic web, the glowing filaments of galaxies ride within far larger, thicker strands of dark matter like pearls strung along invisible cables. The voids, too, are not entirely empty. They likely contain thin traces of this unseen material, but at a much lower density. The web is therefore not just a pattern of light, but a scaffold of gravity whose main ingredients cannot be touched or seen directly. This strange material reveals itself only through its influence on motion and on the bending of light. When a large cluster of galaxies sits in front of more distant objects, the light from those background sources curves around the cluster on its way to an observer. Space itself is warped by the total mass, both visible and dark, and so the images of distant galaxies appear distorted into arcs, rings, or smeared streaks. By measuring these distortions, astronomers weigh the invisible mass, finding again and again that the bulk of the cluster is made of something other than stars and gas. In this way, the darkness between and around galaxies is not just absence, it is a hidden presence that shapes everything else. On even larger scales, another component of the universe reveals itself not through local motions, but through the overall history of expansion. When the brightness of distant supernovae is compared with expectations, the universe appears to be expanding faster now than in the past. This suggests that some form of energy associated with empty space itself is pushing galaxies apart, a phenomenon often labeled dark energy. It behaves very differently from matter, whether ordinary or dark. Instead of clumping into structures, it remains smooth, filling space uniformly and its effect becomes stronger as the universe grows larger. In current models, this dark energy dominates the total energy budget of the cosmos, accounting for roughly 2/3 of the whole, while dark matter contributes most of the remaining third, and ordinary matter supplies only a small fraction. The familiar web of stars and gas floats in this view on a deep sea of invisible influences. The luminous parts of galaxies form only a thin film on top of a far more massive and inscrutable foundation. The idea that most of the universe consists of substances that cannot be directly perceived is unsettling and oddly calming at the same time. On one hand, it means that the grandest structures seen in telescopes are only hints of a deeper architecture. On the other, it implies a kind of continuity in the emptiness itself. Far from being a simple nothing, the darkness that lies between galaxies has weight pressure and a role in the fate of the cosmos. Over long stretches of time, as expansion continues and accelerates, the filaments and clusters that now form a connected web may drift farther apart. Light traveling between them will take ever longer to cross the growing gaps, until many links in the network fall effectively silent, cut off by distance and redshift. In the very far future, only the closest structures may remain mutually visible, the rest receding beyond reach. From the perspective of a single galaxy, the universe might then appear smaller and more lonely, even though it is the same web, stretched over a greater scale. For now, however, the full pattern still hangs together. The observable sphere contains superclusters that can still exchange light filaments, that still shine across their length, and voids that still balance the structure with their vast, quiet volumes. Every photon that falls onto a detector on Earth carries information from some part of this network, crossing dark spaces that are rich in unseen substance. To weigh the darkness between galaxies is to admit that the most important ingredients of the universe are not the bright islands, but the ocean in which they float. The story of distance and light cannot be told only by counting stars. It must also include the silent scaffolding that holds them, and the accelerating breath of space that pushes them slowly apart. As the view continues to contract toward the Milky Way, this hidden framework will remain in the background, shaping even the local neighborhood in ways that are not immediately obvious, its presence registered only in the paths that stars and light are allowed to take. Inside one arm of the cosmic web, a single spiral galaxy rotates slowly, its disk of stars and gas turning like a pale wheel in the dark. This system, the Milky Way, forms a flattened arrangement of luminous matter about 100,000 light years across, with a dense central swelling and a thinner outer disk. In a side view, such a galaxy would appear as a narrow, bright band crossed by dark lanes of dust, with a faint halo of scattered light above and below. Seen from above, its spiral arms would wind outward from the center, marked by knots of star, forming clouds and young blue-white stars. The Milky Way cannot be viewed from the outside, yet its overall pattern emerges from measurements of stellar positions, motions, and gas emission made all around the sky. These data reveal a central bulge, a thin rotating disk, and an extended halo of stars, all embedded in a larger halo of unseen dark matter. Deep in the bulge near the galactic center lies a compact object whose gravity dominates the inner region. Stars close to this core travel on tight, rapid orbits, their speeds indicating a central mass millions of times greater than that of the Sun. The simplest explanation is a supermassive black hole, a region where matter has collapsed so completely that only its gravitational field remains visible. Around this hidden anchor, the disk of the galaxy turns. Stars and gas nearer the center complete an orbit more quickly than material farther out, yet not in the way a simple spinning wheel would behave. Measurements show that orbital speeds stay high well beyond the radius where most visible matter resides. This flat rotation curve points to the influence of the dark matter halo, whose invisible mass deepens the gravitational well and keeps the outer disk bound. Among the countless stars in the mid-regions of the Milky Way lies the Sun. It orbits the galactic center at a distance of roughly 2/3 of the disk radius within a modest spiral feature often described as a local arm. Interstellar dust clouds in the line of sight block much of the view toward the center in visible light, creating the broken river of brightness and shadow that stretches across the night sky. At longer wavelengths, that dust becomes transparent, and surveys in radio and infrared reveal a continuous ring of emission encircling the sky, thicker toward the galactic core and thinner in the opposite direction. From these surveys and from the sun's speed on the order of a few hundred kilometers per second, astronomers infer that a full orbit around the galaxy requires several 100 million Earth years. Since the solar system formed more than 4 billion years ago, it has completed many such circuits, slowly changing its surroundings as it drifts through different spiral segments and quieter interarm zones. Over these vast intervals, star formation sweeps along the arms. Massive stars live brief, brilliant lives, and supernova explosions enrich the surrounding gas with heavier elements. The disk is therefore not a fixed structure, but a shifting pattern, with stars and clouds continually entering and leaving the bright arms as they orbit. Beyond the disk extends a more diffuse stellar halo containing ancient stars and compact clusters that follow elongated inclined orbits. Some pass far above the disk before plunging back through it, tracing loops that span tens of thousands of light years. Faint streams within the halo reveal the remnants of smaller galaxies pulled apart and absorbed over billions of years. Enclosing both disk and halo, the dark matter component stretches even farther, perhaps several times the visible radius, its exact outline uncertain, but its gravitational effect unmistakable. In the great census of galaxies, the Milky Way appears fairly typical. It is neither among the most massive spirals nor among the smallest, and its overall structure has many close counterparts elsewhere in the universe. Yet for any beings who arise within it, this ordinary spiral becomes uniquely important. Every known story of chemistry, life, and thought unfolds somewhere inside its disk or halo. From a distance, the galaxy would present itself as a single pinwheel of light hanging in the cosmic web, its hundreds of billions of stars blended into a smooth glow. Closer in, that glow breaks apart into individual suns, many of them surrounded by planets. Even if only a small fraction of those systems host stable Earth-like worlds, the total number of potentially habitable planets would still be enormous. The Milky Way thus becomes a container for many possible histories, most of them forever unknown. Despite this richness, the space between stars is wide. Typical separations of several light years mean that each stellar system occupies an isolated pocket of space linked to its neighbors only by the slow travel of light. On any map that shows the whole disk, the solar system shrinks to a point too small to mark. The idea of a home galaxy carries this contrast within it, setting a single small system against the backdrop of tens of thousands of light years. As the perspective narrows again, the focus shifts from the galaxy as a whole to the immediate neighborhood of the Sun, where distances begin to be expressed not only in light years, but in light days, light hours, and light minutes, and where the familiar planets trace their paths inside a tiny fragment of the larger galactic sea. Around the Sun stretches a modest volume of space that astronomers often describe as a neighborhood, a small patch of the galaxy in which nearby stars drift past one another over millions of years. Within a sphere of a few tens of light years, the number of stellar systems is not overwhelming. There are a little more than 100 star systems within about 20 light years, far fewer than an intuitive picture of a crowded star-filled sky might suggest. Between each of these suns yawns a distance of several light years on average, a gulf so large that even light racing at its fixed speed needs years to cross from one house in this neighborhood to another. In diagrams, this local region appears as a sparse cloud of points around the Sun, each point marking a star or a small group of stars. The lines, sometimes drawn between them for clarity, are only symbolic. In reality, there are no bridges or roads. The flow of radiation and charged particles through the thin interstellar medium. The Sun itself moves through this region on its long orbit around the galactic center, while nearby stars follow their own paths, each track slightly tilted and slightly faster or slower than the average, so that on long time scales, the pattern of neighbors slowly changes. The nearest known star to the Sun is a small red dwarf called Proxima Centauri, part of a triple system that also includes two larger, more sun-like stars. Proxima Centauri sits at a distance of a little more than 4 light years. That is close enough that its light leaving in the present will reach the solar system in just over 4 years, yet far enough that a spacecraft traveling at any speed achieved so far by human technology would need many thousands of years to arrive. The Alpha Centauri pair slightly farther away are both bright enough that if they were placed at the sun position in the sky, they would cast intense white daylight. In their true location, however, they appear only as a single bright point from Earth perspective, and Proxima itself is too faint to be seen without a telescope, despite being the closest star of all. Even here, in the region of space where the Sun lives, perception from a planetary surface gives a misleading impression. The sky seems rich in bright stars, yet almost all of the nearest neighbors are too dim to see without instruments. The local neighborhood is dominated not by large luminous suns like the familiar one, but by smaller, cooler red dwarfs. These stars are many times fainter than the Sun, and their light does not stand out against the general glow of the galaxy.
Many of the nearest stars belong to this class. Barnard's star, for example, lies at a distance of a little under 6 light-years. It is another red dwarf, unremarkable in size, yet remarkable in its motion.
When its position is measured over years and decades, it slides noticeably across the sky relative to background stars. This high proper motion reveals that the Sun and Barnard's star are moving past each other along different galactic paths, a reminder that the quiet map of the local volume is not static, but constantly shifting as time passes. Among the local group of brighter stars, Sirius stands out. It lies at about 9 light-years and shines as the brightest star in the night sky from Earth perspective. Sirius is not a solitary object, but a binary system. The main star is somewhat more massive and hotter than the Sun, while its companion is a white dwarf, the dense remnant core of a once larger star. The existence of this compact companion inside the local neighborhood hints at earlier phases of stellar evolution already completed near the Sun, and at many more such remnants likely hidden among faint, undetected objects. When positions, distances, and motions of nearby stars are plotted together, a subtle structure appears. The Sun seems to reside in a low-density cavity of interstellar gas, known as the local bubble, a region where past supernova explosions have cleared out much of the surrounding material. The nearest stars occupy this bubble with the Sun, while denser clouds of gas and more distant stars trace its ragged edges. Within this space, the solar wind from the Sun carves out its own smaller bubble, the heliosphere. The boundary where the solar wind yields to the interstellar medium lies far beyond the outer planets, at a distance measured in light hours or light days, rather than light years, but still deep inside the larger stellar neighborhood. The quiet arrangement of nearby suns raises a simple but unsettling question.
If planets circle many of these stars, and if some of those planets host oceans, atmospheres, and complex chemistry, then there may be many separate histories unfolding in parallel within only a few tens of light years of the Sun. Each world would see the others only as bright points in its own sky, separated by years of light travel time. Signals sent from one to another would arrive as delayed echoes, and any attempt at physical travel would be constrained by the same harsh arithmetic of distance and speed. The neighborhood looks gentle and familiar on a diagram, a loose cloud of dots floating in a modest sphere, yet each dot is wrapped in its own isolation. Light years, even when counted in small numbers, act as firm partitions between these suns, ensuring that for now they remain quiet, neighbors sharing the same arm of the galaxy while hardly touching at all.
Within the soft interior of the local bubble, the solar system hangs like a tiny lantern, its faint sphere of influence almost invisible against the wider star field. At the center burns the Sun, an ordinary yellow dwarf star, whose gravity and light weave together the structure of the system. Around this single mass, planets dwarf planets, moons, asteroids, and comets trace overlapping paths, forming a layered architecture that reaches from the hot, bright inner regions to a remote frontier where the Sun becomes just one star among many. At the human scale, this collection of worlds feels enormous, yet when measured against the arm of the galaxy, it shrinks to a mote of dust. One way to see this contrast is to think in units of light travel time instead of kilometers. From the Earth to the Sun, light needs a little more than 8 minutes. The radius of the main planetary system, therefore, amounts to only a few light hours.
Set against the 100,000 light year diameter of the Milky Way, this is almost nothing, a thin circle etched inside a disk whose full breadth defies easy imagining. The solar system does not fill even a noticeable fraction of the local stellar neighborhood. It is instead a compact family orbiting quietly within a vast shared volume of space. The innermost regions cluster close to the Sun, where 4 small rocky planets circle within the first few light minutes. Their orbits lie roughly in the same plane, a relic of the flattened cloud from which the system formed. Between them and farther out, belts of rubble and dust mark places where planet building never fully completed. Beyond the rocky worlds, giant planets of gas and ice take their courses, each encircled by rings and moons that amount to miniature systems in themselves. A single orbit for the farthest giants spans many Earth decades.
Outside the last giant planet, a broad ring of icy bodies forms what is commonly called the Kuiper Belt, a reservoir of small frozen worlds. Beyond even this zone, theory and indirect evidence suggest a far larger, more diffuse sphere of comets known as the Oort cloud, reaching perhaps a light year or more from the Sun. If such a cloud exists as imagined, its outer edge would mark the point where the gravity of passing stars and the general pull of the galaxy begin to compete seriously with the Sun grip on small objects. In that distant shell, comets would drift slowly, bound only loosely to the solar system. Within this spatial hierarchy lies the heliosphere, the true bubble carved by the Sun. Charged particles from the solar wind stream outward in all directions, forming a wind-blown cavity inside the interstellar medium. Near the Sun, this wind moves swiftly, but as it travels outward, it gradually loses momentum. Eventually, it meets the opposing pressure of the thin gas between the stars and slows sharply at a boundary region often described as the termination shock. Beyond that lies a turbulent zone where the solar wind mixes with the surrounding medium, and still farther out lies the heliopause, the surface where the outward flow of particles effectively ends and the interstellar medium takes over. Probes launched from Earth have spent months crossing this domain. The twin Voyager spacecraft sent outward in the late 20th century have both passed beyond the heliopause, becoming the first human-made objects to enter interstellar space. Yet even now, after nearly half a century of travel at tens of kilometers per second, they remain within less than 1 light day of the Sun. Their progress offers a tangible measure of scale. What seems like a vast journey by the standards of a single civilization still does not carry a spacecraft even 1 light day from its star, while the nearest other star lurks more than 4 light years away. Between the heliopause and the imagined distant edge of the Oort cloud, the environment gradually changes from solar-dominated to galaxy-dominated. Any object occupying this realm would feel the Sun as a bright source, but not the overwhelming presence experienced near Earth. A planet orbiting at such a distance would not be stable. Gravitational nudges from passing stars and from the galactic tide would eventually dislodge it. The layered nature of the solar system thus follows from the competition between gravity of the Sun and the surrounding galaxy. Closest in the star, winds easily binding planets and moons tightly. Farther out, the binding weakens, and small bodies inhabit marginal orbits, easily perturbed. At the very edge, membership in the system becomes ambiguous and objects may drift away forever. All of this structure, from the inner rocky worlds to the distant cometary halo, fits inside a bubble that is, in terms of light travel time, tiny. The Sun contribution to the galaxy, when measured in light hours and light days, occupies a volume that could be crossed by light in less than a year. The fact that planets and comets orbit within this miniature domain while the galaxy stretches for tens of thousands of light years around it highlights the enormous gulf between local and galactic scales. As the viewpoint continues to contract, the attention turns from this compact but intricate system as a whole to one particular orbiting world where distances can finally be felt in human terms, and the unit of the light second begins to shape everything from communication delays to the rhythm of exploration missions. Around one small planet in this spiral galaxy, distances become small enough that light begins to sketch a more familiar geometry. Earth spins within the thin band of the solar system, wrapped in an atmosphere, surrounded by artificial satellites and accompanied by a single large moon. In diagrams, the pair appears close separated by a gap that seems narrow compared with the orbits of outer planets, yet even here, light does not move instantly. From the surface of Earth to the surface of the moon, a beam must travel for a little more than 1 second. In that brief span, it crosses almost 400,000 kilometers of empty space. The term light second describes this distance. It is the span that a ray of light covers in 1 second when moving at its fixed speed of about 300,000 kilometers per second. A ring centered on Earth with a radius of 1 light second would just reach out almost to the lunar orbit and partway back. For the human mind, which usually measures movement in steps, car journeys, or flights that last a few hours, 1 light second is already a surprising unit. In that same second, an aircraft might cover only a small fraction of a kilometer. A person walking briskly would barely have shifted position. The idea that between Earth and Moon there stretches a gap that light itself needs more than a full second to cross begins to break the illusion of immediate connection. During the Apollo program, signals from astronauts on the lunar surface traveled as radio waves at light speed back to receiving dishes on Earth. Their voices converted into patterns of electromagnetic energy left antennas near the moon and reached the home world about 1 1/3 seconds later. Controllers responded and the reply made the reverse journey so that every exchange contained a built-in pause of almost 3 seconds. Recordings from those missions revealed this subtle rhythm. After a statement from the moon, a short silence follows. While the signal crosses space, then a response arrives after another delay. The conversation remains intelligible and natural, but the small gap stands as a constant reminder that even across this relatively modest distance, space insists on being counted in units of light travel time. The Earth-Moon system also illustrates how light seconds become tangible in other ways. When the moon reflects sunlight toward Earth, the photons that left the sun took about 8 minutes and 20 seconds to reach the orbit of Earth, then a further one and a bit seconds to bounce from the lunar surface to the eyes of observers. The image of the moon seen in a clear night sky is therefore already an echo. It shows the state of that distant surface as it was slightly more than 1 second earlier, lit by sunlight that reveals the condition of the sun several minutes in the past. Time and distance in this simple nightly view cannot be separated. They combine into a layered picture in which even nearby objects are seen as they were, not as they are, in the same instant. Around Earth itself, many artificial satellites circle at altitudes measured in tens of thousands of kilometers at most. For them, light travel times are tiny fractions of a second. Navigation systems, climate satellites, and communication constellations rely on the assumption that signals cross these distances almost instantly. Yet even here, engineers must account for the small but real delay. The Global Positioning System, for example, determines locations on Earth by comparing the arrival times of signals from multiple satellites whose positions and onboard clock readings are known. Those signals travel at light speed. A mismatch of only a few billionths of a second in timing would translate into errors of meters on the ground. As a result, the system must correct for delays due to both distance and relativistic effects, such as time dilation from the satellite's speed and their position higher in Earth gravitational field. Without these corrections, the mapping between light time and physical distance would become blurred, and the system would slowly drift out of alignment with reality. The concept of a light second thus becomes an invisible ruler wrapped around Earth, calibrating every precise measurement of position and motion. The presence of the moon also introduces the idea of light travel time into everyday technology in another way. Radio waves used for communication can bounce off the lunar surface and return to Earth, a practice known as Earth-Moon-Earth communication. In such experiments, an operator sends a powerful radio pulse upward. The signal travels to the moon, reflects off the regolith, and returns to a receiver on Earth. The round trip takes a little under 3 seconds. The echo that arrives is delayed, distorted, and faint, but unmistakable. With each pulse, the planet hears its own voice, returning from 250,000 miles away, translated into more careful language as a few 100,000 kilometers. That echo makes the abstract idea of a light second feel almost tangible. It is the time it takes for the world to ask a question of its moon and hear the response. Weather patterns and the dance of oceans unfold on scales where light speed overwhelms any sense of delay. Sunlight scattered in the atmosphere or reflected from clouds and water reaches sensors and eyes so quickly that the mind experiences the change as immediate. A storm front may move over hundreds of kilometers in a day, but light mapping that movement from above does so with a lag that is measured in thousandths of a second. In this regime, the finitiness of light speed disappears beneath human perception.
It is only when distances reach planetary or lunar scales that the gap becomes visible in the rhythm of signals. In the context of Earth and Moon, light seconds remain countable. One, two, three, enough to notice, but not so many as to detach cause from effect. Commands sent to a spacecraft in lunar orbit or to a lander on the far side require patience, yet not the deep patience needed for missions farther away. In this sense, the Earth Moon system is a threshold region where the human intuition of immediacy begins to fray but has not yet fully broken. Beyond the orbit of the moon, as missions venture outward toward Mars, the outer planets, and eventually the boundary of the heliosphere, light seconds accumulate into light minutes and light hours, stretching the delay until no real time interaction is possible. The gentle arithmetic first felt between Earth and Moon becomes decisive, turning distance into a barrier for communication as much as for travel.
The quiet gap that light crosses in a little more than 1 second between planet and satellite is therefore not just a local curiosity. It is the first rung on a ladder of light, defined distances that will step by step redefine what proximity and remoteness mean in the wider solar system. Within the band of space between Earth and Moon, the unit of the light, second, still touches human intuition. Beyond that band, the same unit begins to stretch perception until it almost breaks. On the surface of Earth, distance is usually measured in meters, kilometers, and perhaps in the size of a city, a country, or a continent. A person who walks at a comfortable pace might cover a few kilometers in an hour. A car on a highway can travel about 100 kilometers in that same hour. A commercial aircraft high above the clouds may cross close to 1,000 kilometers in an hour. These speeds feel familiar in daily life. When they are compared directly with the speed of light, a quiet sense of mismatch appears. The distance that light covers in a single second, about 300,000 kilometers, is so great that even the fastest aircraft takes many days to trace an equivalent path. A car traveling at 100 kilometers per hour would need about 3,000 hours to cover 300,000 kilometers. That span translates to roughly 125 days of continuous driving. A jet moving at close to 1,000 kilometers per hour would still require more than 300 hours, which is almost 2 weeks of uninterrupted flight. Even the circumference of Earth, roughly 40,000 kilometers, is tiny compared with the light second. A beam of light could circle the planet a little more than 7 times in 1 second. In the time it takes for a heartbeat, light could run laps around the world, while any vehicle built so far would scarcely have moved.
In this comparison, everyday motion becomes almost motionless on the cosmic scale. The step from a light second to a light minute multiplies distance by 60. A light minute spans about 18 million kilometers. On this scale, the entire Earth-Moon system shrinks to a small knot near one edge of a vast circle. For a car, such a distance is simply impossible. At 100 kilometers per hour, covering 18 million kilometers would require many tens of thousands of hours of continuous driving. Even an aircraft limited to close to 1,000 kilometers per hour would need well over 2 years to travel the span of a single light minute. The step from a light minute to a light hour introduces another factor of 60. A light hour at about 1,080,000,000 kilometers embraces much of the planetary region around the Sun. The fastest spacecraft yet, launched traveling at tens of kilometers per second, take many months to move through similar distances.
At speeds familiar from commercial jets, a light hour would be utterly out of reach, requiring centuries of continuous flight. The latter continues from light hours to light days, then to light weeks and light months. Each step multiplies the previous scale again by roughly 24 or by 7 or by 30, depending on the chosen unit of time. A light day about 25,900,000,000 kilometers is large enough to contain the entire region currently reached by the most distant probes. Voyager 1, after almost half a century of uninterrupted flight, has traveled roughly this distance from the Sun. When its radio messages arrive at Earth, they have spent about 1 light day crossing the intervening space. The time delay is noticeable in operations, yet the distance remains within a shell so small relative to a light year that it hardly registers on galactic maps. From the standpoint of human experience, the distances climb when moving from kilometers to light seconds. Minutes and hours already feel overwhelming. From the standpoint of a spiral galaxy, they are minor increments inside a tiny cell. The repeated multiplication by factors of 60 and 24 quickly creates numbers in the millions and billions. These numbers are large enough that the mind can no longer connect them to any concrete scene. It can recite them or write them down, but it cannot picture them. To ease this strain, analogies based on time often help. 1,000,000 seconds amount to a little more than 11 days. 1,000,000,000 seconds correspond to more than 30 years. In a similar way, each new step up the ladder of light-defined distance pushes the imagination farther from daily experience. The concept of a light second still allows some intuitive grasp. The concept of a light minute begins to strain it. A light hour and a light day push beyond the reach of everyday imagination, and a light year lies still farther along this road. When astronomers speak of a star being 4 light years away, or a galaxy being millions of light years distant, they are calling on units built from this same ladder, extended far beyond the point where meters or kilometers are useful. The light second that measures the gap between Earth and Moon becomes the basic step. Light minutes measure the distance to the Sun and to nearby planets. Light hours and light days describe the outer architecture of the solar system. Light years and greater multiples then take over for the space between stars and galaxies. At each level, the same constant speed of light silently ties together time and distance. The familiar human scales occupy only the first few rungs of this ladder, and beyond them stretches a hierarchy of distances where no direct physical journey has yet taken place, but where light has been traveling all along, carrying information outward and inward in a continuous patient flow. Long before anyone speaks of light years or cosmic horizons, light itself seems immediate. Eyes open and starlight appears in an instant. A flame is lit and walls and faces emerge without any sense of delay. For most of human history, it is natural to assume that light simply happens as though sight were a direct contact between observer and object. Philosophers in ancient cultures debate whether vision arises from rays that leave the eye or from something emitted by the object. Yet the thought that light might take measurable time to move hardly appears. On the familiar scale of houses and fields, the speed of light is so great that it masquerades as infinite. Only when distances grow planetary does its finiteness begin to show, and the first hints appear not in laboratories, but in the 17th century, astronomers timed the eclipses of the moons of Jupiter, using them as celestial clocks. One of them, a Danish observer named Ole Rømer, notices a quiet irregularity. When Earth moves closer to Jupiter along its orbit, the predicted eclipses seem to occur a little earlier than expected. When Earth moves farther away, the same eclipses arrive late. The differences are small, measured in minutes, but they repeat and follow Earth position around the Sun. The orbits of the moons themselves remain steady. Something else must be adding or removing delay. Romer proposes a simple answer that changes the understanding of light. If light requires time to travel, then the interval between an eclipse and its observation on Earth will depend on how far the light has to go.
When Earth is nearer to Jupiter, the path is shorter and the event is seen earlier. When Earth is farther away, the path is longer and the event is seen later. By tracking how much the timings shift as Earth moves from one side of its orbit to the other, Romer estimates how long light takes to cross that orbital diameter. His numerical value is rough because the size of the orbit is not yet well known, but the conclusion is clear. Light is not instantaneous. It moves with a finite speed. From this realization flows a new way of thinking about distance. If light has a definite velocity, then every observation is an observation of the past. The Sun is seen as it was several minutes ago. Jupiter is seen as it was nearly an hour ago. Distant stars are seen as they were years or centuries ago. Space and time are no longer separate. Every extra step of distance adds another slice of time to the journey of light.
In the centuries that follow, experimenters on Earth refine this speed with instruments rather than planets. In one classic approach, a beam is sent toward a distant mirror and returned while a rotating wheel or mirror repeatedly opens and blocks the path. By adjusting the rotation until the returning beam is just cut off, and by knowing the distance to the mirror, investigators infer how long the light was away. Later spinning mirrors deflect a beam over slightly different angles, depending on how much they turn, while the light travels out and back. In still later work, microwave signals and laser pulses cross known baselines, and electronic instruments time their journeys with great care. Each method arrows the uncertainty until the speed of light is pinned down with high precision, close to 300,000 kilometers per second. With that constant in hand, distance can be defined by time. A light second is the distance light travels in 1 second. A light minute, a light hour, and a light year follow the same rule. The names change, but the idea remains simple. Space becomes what light can reach in a chosen duration. This viewpoint fits naturally with the behavior of electromagnetic waves, and the mathematics of electromagnetism deepens it. When the equations of electric and magnetic fields are written in the 19th century, they contain a preferred speed. They say that ripples in those fields propagate at a particular rate, and that this rate matches the measured speed of light. Light is recognized as an electromagnetic wave, not as a separate kind of substance, and the presence of a fixed speed inside the theory suggests that light travel time is a built-in feature of nature. The last step in this chain arrives when that speed is taken as a universal rule rather than a property of one kind of radiation.
If the speed of light is the same for all observers, no matter how they move, then it can serve as a benchmark for space and time themselves. In the early 20th century, Albert Einstein asks what the world must look like if every observer always measures the same speed for light. The answer is strange but precise. Measurements of distance and duration must adjust so that for light, the ratio between them never changes. Links along the direction of motion contract. Time intervals lengthen or shorten depending on relative speed. Events that seem simultaneous to one observer may not be simultaneous to another. Out of these requirements emerges the theory of special relativity, in which the speed of light is woven into the geometry of space-time itself. Within this framework, there is no way to send any influence faster than light without tearing that geometry and breaking the usual order of cause and effect.
The finite speed that first reveals itself in the timing of eclipses and mirror experiments therefore turns into a limit that shapes what kinds of signals and journeys are possible. The universe does not merely contain light that moves quickly. It uses the speed of light as a buoy for how distances and intervals fit together. The recognition that light is not instantaneous marks the beginning of understanding that every act of seeing is also an act of looking backward in time by an amount measured in seconds, minutes, years, or light years, depending on how far the light has had to come. From the moment the speed of light becomes a measured constant rather than an assumption, distance quietly gains a new definition. Instead of being only a matter of rulers and chains stretched over terrain, distance turns into time multiplied by that constant speed. A second of travel at light speed defines a light second, a minute defines a light minute, and by extension, a year of continuous travel defines a light year. This year is not a vague interval of changing seasons, but a carefully counted span of days, hours, minutes, and seconds. In this sense, a light year is simply the path that light traces through space while clocks tick steadily from one moment to another, a full cycle around a star. To turn that idea into a number, astronomers begin with the measured speed of light in vacuum about 300,000 kilometers per second. They then count how many seconds fit into a year. There are 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, and 365 days in a standard year. Each of those seconds carries light another 300,000 kilometers along its path. When all the multiplications are combined, the result is a distance of roughly 9,460,000,000,000 kilometers. That total is what is meant by 1 light year, the length of the trail that a beam of light draws through empty space in the time it takes a planet like Earth to complete a single orbit around its star. The numeric value is enormous, but as a bare figure, it offers little help to intuition. 9,460,000,000,000 kilometers is easy to write and to recite, but the mind quickly loses any sense of its scale. To regain some feeling for its size, the number can be broken into familiar steps. A single kilometer is a distance that a person can walk in about 10 or 12 minutes at a relaxed pace. 1,000 of those distances make 1,000 kilometers, roughly the span of a long journey in a fast vehicle. 1,000,000 kilometers already exceeds the circumference of Earth many times over. 1 billion kilometers would carry a spacecraft well out past the orbit of Mars. The leap from 1 billion to 1 trillion repeats the pattern. Each step multiplies by 1,000. 1 million is 1,000 thousands, 1 billion is 1,000 millions, and 1 trillion is 1,000 billions. When that trillion is multiplied by almost 10, and when several hundred additional billions are added on top, the compound figure moves far beyond any length that has ever been traveled by a human vehicle. Time-based analogies help again. One way to picture 1 trillion is through counting. If someone were to count one number every second without resting, it would take more than 31,000 years to reach 1 trillion. The contrast between the slow pace of counting and the speed of light makes the size of the unit clearer. A light year does not mark the distance to the nearest star or the size of a galaxy.
It is instead a basic rung in the hierarchy, already immense but still small compared with the separations that actually exist between celestial objects. Proxima Centauri lies a little more than 4 such units away from the Sun. The center of the Milky Way lies tens of thousands of light years distant. Galaxies and neighboring clusters sit millions of light years apart. The observable edge of the universe lies tens of billions of light years away in present distance. Every one of these spans is measured by repeating the basic step of the light year over and over. To make the light year approachable, astronomers sometimes translate large terrestrial distances into fractions of it. The circumference of Earth, for example, is a little more than 40,000 kilometers. Light would run around that circle more than 7 times in a single second, and many millions of times in a day. Yet even after an entire year of such motion, the distance covered is only 1 light year, and that is only a modest jump into interstellar space. Beyond perhaps a couple of light years, the gravitational pull of the Sun fades and the realm becomes that of the galaxy as a whole. The light year then marks a bridge between the local scale of a planetary system and the broader scale of stellar neighborhoods. It is large enough that numbers for star-to-star distances remain manageable, yet it stays directly grounded in a physical process, the steady, unwavering motion of light across emptiness. There is a quiet elegance in this choice of unit. Unlike kilometers or miles, which must be defined by an arbitrary rod or by a fraction of a planetary circumference, the light year arises from a constant of nature. Any civilization able to measure the speed of light and to track the passage of time could in principle define the same unit, even if its home world were larger or smaller than Earth. The light year embodies the link between the structure of space-time and the methods used to chart it. It captures in a single phrase both how far light travels and how long that travel takes. As such, it becomes not just a practical tool for measuring cosmic distances, but also a reminder that to look far out into space is always to look far back into time, following the trail of photons that have been in flight for years or for centuries before finally arriving at a waiting mirror or eye. As soon as the speed of light becomes a fixed part of nature rather than a mere measurement,
It begins to shape the rules of motion in unexpected ways. In everyday life, speeds add in a simple pattern.
A person walks forward inside a moving train, and an observer by the tracks sees the total speed as the sum of the train speed and the walking speed. This rule seems obvious because at familiar velocities it works extremely well. Yet, if that same simple addition were applied at very high speeds, it would allow light to be overtaken. A fast enough rocket could shine a beam forward, and in the simple picture, an outside observer would see the beam moving faster than light. Experiments do not support this. No matter how quickly a source moves, its light always travels at the same speed. This insistence from nature forces a revision of what distance and time mean. In the early 20th century, Albert Einstein frames a new principle. The laws of physics should look the same for all observers who move at constant speeds relative to one another, and the speed of light in vacuum should be the same for all of them.
There is no preferred stage, no hidden ether that defines